students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as ionic. Today let's try to find out the relationship between hydrolysis constant, ionic product of water and dissociation constant. Let's try to find relation between hydrolysis constant ionic product of water and dissociation constant. Right. First, let us consider a salt of strong acid and weak base. Let us consider salt of strong acid and weak base. Let us assume that Ba is a salt of strong acid and weak base which undergoes hydrolysis. Ba is a salt of strong acid and weak base which undergoes hydrolysis. To give weak base and hydrogen ion. Weak base and H plus ions. Right? Now, I can say that the solution at equilibrium Ba undergoes hydrolysis to give you BOH plus HN. Fine, do you get this in here? So this is your salt, this is base, and this is acid. This is your weak base, and this is strong acid. Okay. Now the ionic reaction for this will be Ba will dissociate to give you B plus plus A minus. Water is present in excess quantity, so it will remain as it is. Right? BOH is weak base, therefore this will not dissociate. HA, which strong acid, will give you H plus plus A minus. A minus gets cancelled, so I'll get B plus plus H2O gives you BOH plus HA, H plus, sorry. Right, now if I apply law of mass action to this, by applying law of mass action, I can say that dissociation constant is active mass of the product upon active mass of the reactant, that is active mass of BOH into H plus upon active mass of the reactant, that is B plus into H2O. I can take H2O on the other side, so K into active mass of H2O will give you active mass of BOH into active mass of H plus upon active mass of B plus. Right? But K into H2O gives you KH, but K into active mass of H2O will give you KH, which is your hydrolysis constant. Therefore, I can say that hydrolysis constant for this equation is going to be BOH into H plus upon B plus. Right? Once I have this, then I can say that call this as equation 1. I can say in the same solution two more equilibria exist. In the same solution two more equilibria exist. Right? One is for water. I can say water, since water is a weak electrolyte, It ionizes slightly since water is a weak electrolyte. It ionizes slightly. So water ionizes slightly to give you H plus plus OH minus, right? In which case I can therefore say that ionic product of water is active mass of H plus into active mass of OH minus, right? Similarly, let's consider the weak base. This was for water, and then you have for weak base. The weak base will also ionize slightly. This is similarly the weak base also ionizes slightly. So in which case I can say BOH is the weak base which ionizes slightly to give you B plus plus OH minus, right? In that case, dissociation constant for this base, if I apply law of mass action, will be active mass of the product upon active mass of the reactant. So active mass of the product upon active mass of the reactant, right? Now we will call ionic product of water as equation 2 and dissociation constant of the base as equation 3. Now consider Kw upon Kb. Let's find out the ratio of ionic product of water to dissociation constant of the base. Ionic product of water is H plus into OH minus divided by dissociation constant of the base, that is B plus into OH minus upon BOH, right? OH minus gets cancelled. That will give you Kw upon Kb. That will give you Kw upon Kb is equal to H plus upon B plus denominator of denominator becomes numerator BOH, but BOH into H plus upon B plus is nothing but KH. So I can therefore say Kw upon Kb is equal to KH. This is the relationship between hydrolysis constant, ionic product of water and dissociation constant. In this chapter these were the three constants we have found out, and this is the relationship between them. Fine, do we get this thing here? Now this is for a salt of strong acid and weak base. Now let us consider for a salt of weak acid and strong base. Salt of weak acid and strong base. Exact replica of the previous theorem. You will say let Va be a salt of weak acid and strong base which undergoes hydrolysis to give weak acid and OH ions, right? I can say that the solution at equilibrium will be Va hydrolyzes reversibly to give you BOH plus HA. This is your salt. This is weak acid and this is strong base. Right? Once you have this, then I can say that the ionic reaction for this will be B plus plus A minus dissociates. Salt dissociates, water does not dissociate, it ionizes. Strong base dissociates. Weak base ionizes, so it will not dissociate here. So in that case, your B plus will get cancelled, so you will get A minus plus H2O. Reversibly gives you OH minus plus HA by applying law of mass action. Law of mass action. I'll get dissociation constant as active mass of the product upon active mass of the reactant, A minus into H2O, right? So in which case I can therefore say that K into H2O will give you OH minus into HA upon A minus. K into H2O, but K into active mass of H2O is nothing but KH, which is your hydrolysis constant. So in which case you can say that KH is equal to OH negative into HA upon A negative. Call this as equation 1. Now I can say in the same solution two more equilibria exist. In the same solution two more equilibria exist. One for water. I can say that since water is a weak electrolyte, it ionizes slightly, right? So water ionizes slightly to give you H plus plus OH minus. Therefore I can say that ionic product of water is active mass of H plus into active mass of OH minus. Call this as equation 2. Now we also have a weak acid. For weak acid I can say that similarly weak acid also ionizes slightly. Similarly weak acid also ionizes slightly. Now weak acid HA will ionize slightly to give you H plus plus A minus. So if I apply law of mass action, I will get dissociation constant of acid is going to be active mass of the product upon active mass of the reactant. Right? Now consider, call this as equation 3. Consider Kw upon Ka. Kw upon Ka is going to be nothing but H plus into OH minus upon Ka is nothing but H plus A minus upon HA. H plus gets cancelled, denominator of denominator becomes numerator, so I will get Kw upon Ka is going to be nothing but OH minus into HA upon A minus. But this is nothing but your KH, so therefore I can say that Kw upon Ka, therefore I can say that Kw upon Ka is equal to KH. That is your relationship between hydrolysis constant, ionic product of water, and dissociation constant of acid for a salt of weak acid and strong base. Now let us consider for a salt of weak acid and weak base. Salt of weak acid and weak base. I can say let Va be a salt weak acid and weak base, which undergoes hydrolysis. Right? I can say that the solution at equilibrium will be Ba, will undergo hydrolysis to give you BOH plus HA. This is salt, this is weak base, and this is weak acid. Right? In ionic form, the reaction will be B plus, will dissociate A minus, the salt dissociates to give you B plus A minus. Water ionizes, will not dissociate. Weak base will not dissociate. Weak acid will not dissociate. Right? Straight away I can apply law of mass action to this by applying law of mass action. I can say that dissociation constant is active mass of the product, that is BOH into HA upon B plus A minus into H2O. Cross multiply, H2O goes on the other side, so K into H2O will give you BOH into HA upon B plus into A minus. But I can say that dissociation constant into active mass of water is hydrolysis constant KH, which is hydrolysis constant. So in which case I can therefore say that hydrolysis constant KH is going to be nothing but BOH into HA upon B plus into A minus. Right? Once you have this, I can say in the same solution 3 more equilibria exist. One is for water. For water, I can say since water is a weak electrolyte, it ionizes slightly. So H2O ionizes to give you H plus plus OH minus. So this ionic product of water will be active mass of H plus into active mass of OH minus. Then I can say for weak acid, replica, all the 3 derivations are replica of each other. For weak acid, I can say similarly weak acid also ionizes slightly. Weak acid also ionizes slightly. So weak acid HA ionizes slightly to give you H plus plus A minus. Right? Therefore dissociation constant of acid is active mass of the product upon active mass of the reactant HA. Right? Next, I can say for weak base, I can say similarly weak base also ionizes slightly. So I'll have BOH ionizes slightly to give you B plus plus OH minus. So that will give you dissociation constant of base is going to be B plus into OH minus upon BOH. Right? Now consider the equation Kw upon Ka into Kb. Kw is going to be nothing but H plus into OH minus upon Ka. Ka we found out is H plus into A minus upon Ha, and Kb is nothing but B plus into OH minus upon BOH, right? H plus gone, OH minus gone. Denominator of denominator becomes numerator, in which case you will get Kw upon Ka into Kb is Ha into BOH upon A minus into B plus. But that is nothing but your hydrolysis constant. So Kw upon Ka into Kb is nothing but Kh. That is your relationship between hydrolysis constant, ionic product of water, and dissociation constant for a salt of weak acid and weak base. Right? Now let's start with the numericals. People, take down the numerical. Let's see numericals. Take down. Calculate the hydrolysis constant. Calculate the hydrolysis constant, degree of hydrolysis. Calculate the hydrolysis constant, degree of hydrolysis, and pH of 0.02 molar potassium cyanide solution. Potassium cyanide solution if Ka is 1.8 into 10 raised to minus 5 and Kw is 1 into 10 raised to minus 40. Now, potassium cyanide, KCl on hydrolysis. KCl on hydrolysis will give you KOH plus HCl. Right, this is your salt, potassium cyanide. KOH is going to be your strong base. It gives you strong base, and it gives you a weak acid, hydrogen cyanide. So that means potassium cyanide is a salt of strong base and weak acid. Since it is a salt of strong base and weak acid, therefore I can say that its hydrolysis constant will be given by the formula Kw upon it is weak acid, so Ka, right? Do we get this thing clear? So substitute this, so you will get your hydrolysis constant as Kw 1 into 10 raised to minus 14 upon Ka 1.8 into 10 raised to minus 5. Substitute and solve this, you should get this answer as 5.556 into 10 raised to minus 10. So your hydrolysis constant is going to be 5.556 into 10 raised to minus 10. But hydrolysis constant, we had done this derivation also, the relationship between hydrolysis constant and degree of hydrolysis. For a salt of weak acid and strong base, hydrolysis constant is equal to H square C. Hydrolysis constant is equal to square of the degree of hydrolysis into concentration. Therefore, I can say that H is Kh upon C under root. So I'll get H is square root of Kh. You found that out as 5.556 into 10 raised to minus 10 upon C. C is given to you as 0.02. So when you solve this, you should get this answer as your hydrolysis degree of hydrolysis will be 1.66 into 10 raised to minus 4. Right? Next, now potassium cyanide is a sort of strong base and weak acid. Now, since it is a salt of strong base, since KCl is a salt of strong base, therefore I can say that the hydroxyl ion concentration will be equal to Hc base. Therefore I have taken hydroxyl concentration, so that means the hydroxyl ion concentration is H 1.666 into 10 raised to minus 4 into 0.02. When you solve this will be nothing but 3.332 into 10 raised to minus 6 moles per decimeter cube. Once you find this, then you can find out pH. You will get POH. POH is negative log to the base 10 of hydroxyl ion concentration. Right? This sum practically uses everything that you have done in the chapter. Right? So that's going to be negative log to the base 10 of 3.332 into 10 raised to minus 6. Right, this can be written as negative log to the base 10 of 3.332 negative log to the base 10 of 10 raised to minus 6. Right, so in that case this is going to be 0.5227 minus into minus plus 6 log 10 to the base 10 is equal to 1. So you will get your value of POH as 5.4773. But they haven't asked you to find out POH, they've asked you to find out pH. I can say but POH plus pH is 14 pH scale. Therefore I can say that pH is 14 minus POH. So you will get your value of pH as 8.5227. Right? So that's how you will get all the values. You found out all the values. You found out hydrolysis constant, degree of hydrolysis. They asked you to find out hydrolysis constant, degree of hydrolysis and pH. All the three values you have. Fine, do we get this thing clear? Right? Yes, you want to ask me something?
So can't we find out pH directly?
pH I cannot find out directly because here it is strong base. So it is the base that will dissociate and acid that will ionize. If it is whatever is strong, you find that out first and then you find the other one. Right? You will not have, theoretically speaking, there is going to be very little ions that will ionize of acid. And there will be large number of dissociated ions of the base. That's the reason you find out pOH first. Right? Take out next one please. Calculate the degree of hydrolysis. Calculate the degree of hydrolysis of 0.02 molar. Calculate the degree of hydrolysis of 0.02 molar ammonium acetate solution. Calculate
0.02.
0.02 molar ammonium acetate solution, where Ka is equal to Kb is equal to 1.8 into 10 raised to minus 5 and Kw is 1 into 10 raised to minus 14. Right? Now, first of all, I can say that ammonium acetate. Ammonium acetate, I can say on hydrolysis will give you ammonium acetate CONH4 on hydrolysis will give you, this is your salt, it will give you acetic acid CH3COH plus ammonium hydroxide NH4OH, right? So that is going to give you a weak acid and this is a weak base, right? That means ammonium acetate is a salt of weak acid and weak base. Since it is a salt of weak acid and weak base, therefore I can say, once you come to know what kind of acid and base it is, then you can say that therefore KH is going to be KW upon Ka into Kb. That's my equation for salt of weak acid. That's my equation for salt of weak acid and weak base, right? Yes, you want to ask me something, right? So therefore I can say KH is 1 into 10 raised to minus 14 upon Ka. Ka and Kb is given to you as 1.8 into 10 raised to minus 5 the whole square, because Ka is equal to Kb. Now when you solve this, you will get your value of KH to be 0.3086 into 10 raised to minus 4, right? So I've got this. Now since this is a salt of weak acid and weak base, I can say also for weak acid and weak base KH is equal to H square. Hydrolysis constant is equal to square of degree of hydrolysis. So I'll get therefore H is square root of KH square root of 0.3086 into 10 raised to minus 4, right? So in which case you will get this answer as 5.556 into 10 raised to minus 3. That is going to be my hydrolysis constant. These were the only two things asked in this sum. Next, take on the next sum please. The degree of hydrolysis of 0.1 molar, the degree of hydrolysis of 0.1 molar solution of ammonium chloride is 7.46. Calculate the hydrolysis constant and the dissociation constant. Calculate the hydrolysis constant and dissociation constant of the base. Calculate the hydrolysis constant and dissociation constant of the base if Kw is 1 into 10 raised to minus 14. If Kw is 1 into 10 raised to minus 14. Now first of all we are taking solution of ammonium chloride. I can say that ammonium chloride on hydrolysis, ammonium chloride on hydrolysis will give you hydrochloric acid and ammonium hydroxide. This is your salt, hydrochloric acid, strong acid, ammonium hydroxide, weak base. That means ammonium chloride is a salt of strong acid and weak base. Since it is a salt of strong acid and weak base, therefore I can say that KH is going to be nothing but Kw weak base, Kb, right? Now Kw I know, I do not know KH, I do not know Kb. Have they given me? No, they haven't given me. So since I don't know this, first I'll have to use the formula KH is equal to H square C. I'll have to first use the formula hydrolysis constant is square of degree of hydrolysis into concentration. Therefore, I can say that KH is equal to, H is given to you as 7.46 into 0.1, right? So when you multiply this, just make that correction. Hydrolysis constant is 7.46 into 10 raised to minus 5. Please make the correction in the sum. Hydrolysis constant is 7.46 into 10 raised to minus 5 into 0.1. Right? So when you solve this, you will get this answer as 5.564 into 10 raised to minus 10. That's my hydrolysis constant. Once I have my hydrolysis constant, then I can say KH is equal to KW upon KB, weak base. KH I know, KW I know, I can find out KB. KB is going to be 1 into 10 raised to minus 14 upon 5.564 into 10 raised to minus 10. You will get your value of KB to be 1.797 into 10 raised to minus 5. So we found out KB also. These were the two things they had asked you to find out: hydrolysis constant and dissociation constant. Right? Take the next one, please. The pH of 0.1 molar sodium acetate solution, the pH of 0.1 molar sodium acetate solution is found to be 10.6. Calculate the degree of hydrolysis and the hydrolysis constant. Calculate the degree of hydrolysis and the hydrolysis constant. Sodium acetate on hydrolysis. Sodium acetate on hydrolysis, CH3CONA on hydrolysis will reversibly give you, this is your salt, will give you acetic acid CH3COH plus sodium hydroxide. That means it will give you a weak acid and strong base. That means sodium acetate is a salt of weak acid and strong base. Now, since it is a salt of weak acid and strong base, I will have to first find out pOH, because it is the OH ions that will dissociate, right? I cannot do it using pH. So first I'll say pH plus pOH is equal to 14. So in that case I can say 10.6 plus pOH is equal to 14, in which case I will get my value of pOH to be 3.4. But we know that pOH is negative log to the base 10 of OH negative ions. So I can say 3.4 is negative log to the base 10 of OH ions. Take minus sign on the other side. Negative 3.4 is log to the base 10 of OH ions. Take log on the other side. So I can say anti-log. Negative 3.4, guys, can be written as negative 3, negative 0.4. Subtract 1, add 1. It will give you OH negative ions. So this is going to be anti-log of negative 4 plus 0.6 OH negative ions. So this is going to be anti-log of 4 bar 0.6 is OH ions. When you substitute this, you will get this answer as 3.981. OH negative ions is 3.981 into 10 raised to minus 4 moles per decimeter cube. Right? Now, once I have the value of OH ions, I can say that OH ions is nothing but C into H, right? The concentration of OH ions is equal to concentration into degree of hydrolysis. So in which case I should get the value of H from here. H is OH negative upon C. When you substitute, you should get the value of H as 3.981 into 10 raised to minus 3. Right? Once I know H, then I can find out my hydrolysis constant. I can say that hydrolysis constant KH is equal to H square C, but KH is equal to H square C, KH is equal to H, you just found out as 3.981 into 10 raised to minus 3 into C. C is 0.1, right, square. So when you substitute this, you will get your answer as KH is equal to 1.5848 into 10 raised to minus 6. Right? Take our next one, please. Calculate the hydrolysis constant. Calculate the hydrolysis constant, degree of hydrolysis, and pH of 0.1 molar ammonium chloride solution, 0.1 molar ammonium chloride solution if Kb is 1.8 into 10 raised to minus 5 and Kw is 1 into 10 raised to minus 14. Right? Replica of the first sum, I'm not doing this sum, I'll just tell you what this is. This is, they've given you that the solution is ammonium chloride. Ammonium chloride will give you ammonium hydroxide and hydrochloric acid. That means it is going to be a salt of strong acid and weak base. You should be able to do this. Look at your first sum and you should be able to do this. Right? I'll just give you the answer. Two sums I'm giving you all for practice. When you solve this, you should get this answer as answer straight away I'm giving you here. I want you all to try this on your own. KH should be 556 into 10 raised to minus 10. H is going to be 7.454 into 10 raised to minus 5 and pH is 5.127. Those are the values that you should get. Take on another sum, please. Calculate the pH. Calculate the pH of 0.05 molar solution of sodium acetate. 0.05 molar solution of sodium acetate if Ka is 1.8 into 10 raised to minus 5 and Kw is 1 into 10 raised to minus 14. Again, you should be able to do this sum on your own. You are taking sodium acetate. On hydrolysis, will give you acetic acid and sodium hydroxide. That means this is going to be weak acid and strong base again. So you should be able to solve the solution. You should get this answer. Straight away I'm giving you the answer. KH should be again 5.556 into 10 raised to minus 10. H is going to be 1.054 into 10 raised to minus 4 and they've asked you to find out pH. pH is going to be 8.721. Right? That finishes this chapter. We'll stop this here for the day. Thank you very much.